In this lecture class, I'm going to focus on trying to get a quantum mechanically deeper understanding of electromagnetic transitions between atomic states. The material that is discussed here is probably best summarized in the chapter that I wrote on electromagnetic transitions and that is supplied in the learning management system for this course. And then in addition, for a different point of view and a little bit more information on optical transitions, I suggest that Chapter 8 and Appendix K in the textbook by Iceberg and Resnick, and Chapter 12 in the textbook by McGurvey would be useful. The reason that I am going away from the textbook and discussing the quantum mechanical origins and understanding of transitions is that much of our understanding of quantum mechanics is actually based upon experimental observations, and many of the properties that we measure rely heavily on understanding optical spectroscopy of the system that we're looking at. By optical spectroscopy, I mean we measure absorption spectra and emission spectra. We can get other information like polarization and time dependence, but for now we'll just focus on the spectroscopy of the system. So in this section of the lecture, we're going to consider the effect of an electromagnetic perturbation, that is light, on an atomic system. And of course, we'll start out with some idealized one-dimensional systems to get an understanding, and then we'll move on to actually doing some calculations on atomic states. And the ultimate goal here will be to find some of the key rules. They are called selection rules that determine whether and how optical transitions occur. Can we observe them in a given system? I'm going to take essentially two approaches to this. The first gives a good heuristic understanding, I believe, of what is going on when transitions occur. That's a semi-classical approach. Very frequently in quantum mechanics, we start out with a classical analogy and then make substitutions for quantum mechanical operators, as we did with angular momentum. We're going to do something similar here in understanding optical transitions. And then we'll shift into a somewhat more rigorous approximation. So let me start with an approach that I call the sloshing dipole theory. And to summarize the essential physics, an oscillating dipole radiates. So if I have a charge which is oscillating, which is accelerating, that charge will radiate electromagnetic waves. If the dipole actually radiates, then it must lose energy. And then we have the observation from last semester that if we have a mixture of two eigenstates, then that wave function sloshes in the system. I'm going to show an example of that. Therefore, a mixture of two eigenstates is an oscillating dipole. And any perturbation that we apply to a simple system that ends up mixing two eigenstates causes oscillations and therefore causes radiation. And again, if light is coming out of a system, then that must lead to a transition from one state to another. So that's the essential underlying idea. So beginning at the first idea. From electromagnetic theory, we know that an accelerating charge, Q, radiates electromagnetic energy at a rate R, given by rate R is equal to charge squared times the acceleration of the particle squared divided by constants, permittivity of free space and speed of light. So when a particle accelerates, it radiates electromagnetic waves. And in our case, we're going to be worrying about an oscillating charge or a dipole oscillating. So if the charge moves according to position as a function of time is equal to a cosine omega t, then electromagnetic theory tells us, classical electromagnetic theory, tells us that the average rate of emission, so average rate of emission, is charge squared, amplitude of the motion squared, frequency of the motion to the fourth power, and constants, permittivity and speed of light. So let's think about our quantum mechanical states now. So that was our classical start. We know that an oscillating charge radiates. So if we, for example, take the wave function of a particle in a box, the ground state would look like half of a sine function. The first excited state would look like a full wave of the sine function. We add those two together, as I've written here. So now we've created a mixed state, and at time equal to 0 for sine functions, we end up with an overall wave function that looks like this. At some time later on, in fact, 1/2 of an oscillation period of the system, we'll talk about that in a moment, the wave function now looks like this. That is, that the average position for the particle in this box is somewhat to the left of center here, and at a later time is somewhat to the right. So what has happened is that the average position of the particle has moved from here to there. Doing the arithmetic for a wave function which is the result of a particle in a box, adding the first two states, where the time-dependent wave function for one of the two states is the space portion, which was the sine function that I mentioned, times e to the I energy of that state times time divided by Planck's constant over 2 pi over h bar. And so the state itself has a time oscillation portion, but if I square it, then I find that state 1 doesn't move at all. The average position remains fixed. The probability distribution does not change with time. Same for state 2. So for the eigenstates of the system, there is no change in the position of the particle with time. But when I add these two eigenstates together, I get a time dependence that depends upon the energy difference between the two states. I'll come back to define quantities a little bit more carefully in a little. So let's actually do a calculation now for a sloshing dipole. That is, where, for example, I have a positive charge that is fixed at the center of that box, and a negative charge which oscillates from side to side. So we want to find the amplitude of the dipole moment P for the overall mixed state. So we'll calculate the expectation value of the position as a function of time. We're just going to work with one dimension. So overall, I'll just say that the dipole moment is the dipole moment along the x-axis. And that's going to be equal to the charge times the average value of the position for the wave function of the charge. X would be the separation between the two equal and opposite charges in the system to form a dipole. So if I want to find the average position of X, then I perform the standard integral. I have assumed that the wave functions are normalized, so I don't have to normalize this. Charge of the dipole, wave function, operator X, wave function, integrated over all volume. For the simple case where the amplitudes for each of the two states is the same, so I've made an approximation here, then that product x psi star psi looks like this. It's got four terms to it. Psi 1 star psi 1, psi 2 star psi 2, psi 1 star psi 2, and when I do that, I find that the time dependence does not cancel out. The time dependence here canceled out, time dependence here canceled out, multiplying by the complex conjugate causes the time dependent product to be 1. And so my product now, remember I've got an x there, by the way, x in the front of everything, produces complex conjugate of the space portion of wave function 1, space portion of wave function 2, and an oscillation frequency that depends upon the energy difference between the two states. And then continuing the complex product, I get psi 2 star psi 1, and the sign of the exponent has changed here. Okay. For real space wave functions, so let's just make psi 1 and psi 2 real in order to make things simpler for ourselves. That product x psi 1 star psi is equal to my original x psi 1 squared, x psi 2 squared. Remember, this doesn't change at all with time. Once I've squared it, the time dependence has gone away. It is an eigenstate. It doesn't change. But the cross product, with a little bit of manipulation, becomes x times wave function 1, wave function 2, 2 times cosine omega 1, 2 t, where omega 1, 2 is E2 minus E1 over h bar. So that's our frequency of oscillation of the mixed system. That's how rapidly the average charge position shifts from one extreme to the other extreme. Only the time-dependent term, the cosine term, because that's going to be the acceleration, contributes to electromagnetic radiation. So my average radiation, just going back to the equation that I had a few slides back, is the charge on the dipole squared, frequency difference between the two, the frequency of the difference in energies between the two wave functions to the fourth power, constants, and then I've got a spatial integral here, the integral of psi 1, psi 2, x dv integrated over all space squared, right? So looking at this, the average emission rate depends upon the symmetry of the two states that are being mixed. If both states are even, then psi 1 times psi 2 is even, and x times psi 1 psi 2 is odd. The integral of an odd function over all space is going to be 0. If both states are odd, then their product is even, and multiplying by x gives us an odd function. The integral over all space is 0. However, if the two states have different symmetries, for example, one is even and one is odd, then the product is odd, and multiplying by odd x yields an even function. So that has a value. So what this tells us is that we'll only get a transition between two mixed states. That is, that we'll only have a sloshing of the dipole that radiates when the symmetry of the two states that are being mixed is different. One is an even function, the other one is an odd function, for example. To summarize what I just said, if a system's in any mixture of two states, it will radiate energy. So here's my two energy states for the ground state and the first excited state. Now I've mixed them as I did a few slides ago. And this system will radiate because the wave function is sloshing from side to side. If the system is radiating, then energy is being emitted from the system. So let's say I have an equal mixture initially of state 1 and state 2. And that wave function sloshes. Then what's going to happen when I have an equal mixture of the two states, when I start out, the average energy of the system is going to be the average energy of E1 and E2, so I put that in the middle. But because the system is oscillating, and radiating, then what's going to happen is that the average energy of the system is going to decrease. And as the average energy of the system decreases, the probability of finding the system in the lower state of the two goes up. So over time, even though I started with an equal mixture, when I measure later on, I find out that the system is in the lower energy state, is radiated away the energy. So that's the semi-classical argument with respect to what happens when systems radiate. We need a more rigorous theory, and I'm going to summarize it in several slides, in order to understand more of the details of how electromagnetic radiation interacts with atoms and how the radiation actually can be thought of. The interactions can be thought about. So we can ask, why or how do the states mix? And I'm going to answer that question. The radiation itself causes the states to mix. So I might have a system that is in one state, and you say, oh great, it's in an eigenstate of the system. But if there happens to be electromagnetic radiation around, and there always is, that radiation will interact with the system and cause that state that it's in to no longer be an eigenstate of the system and mix it with another state such that a transition can occur. In order to understand this in a little bit more depth, we're going to use time-dependent perturbation theory here. And this is above the level that I expect for this course, but I'm going to run through it so that you get an idea of how we think about this. And then we'll end up with the rules that tell us when and how transitions occur. And for the purposes of this course, we're going to be focused on the rules. So what's the approach here? Our goal in the end is to determine the rate at which a time-dependent perturbing potential, so that's electromagnetic potential wave incident upon an atom, the rate at which that potential causes an electron to jump from one state to another. And the way that we're going to approach this is to look at the known solutions for the system for the atom in the absence of electromagnetic radiation. Then we're going to perturb the Hamiltonian, perturb the energy a little bit by adding in a time-dependent electromagnetic wave. So that's not going to be a big part of the potential. The major part of the potential is the original atomic potential. And then we just tickle the system with an oscillating electromagnetic wave. We look at the solutions of this system in terms of the old eigenfunctions. And by looking at the coefficients as a function of time on the old eigenfunctions, we can determine how the perturbation causes the balance between the old solutions to shift so that we get a transition from one state to another. I've labeled some of these slides. I put a background that is yellow on some of these slides because the mathematics that I'm going through here, or the details that I'm going through here, is not something that I want to explicitly hold you responsible for in this course. So the chapter that I wrote has got more detailed description of what is being done here. I'm going to summarize it and with the understanding, please, that I don't want you to be able to replicate this. I want you to see it now and get some idea of what's going on. So here is our original Hamiltonian, which produces the eigenfunctions and eigenenergies of our original atom. So this is the atomic potential, and these are the wave functions of the atom of interest. Okay, and the atomic potential is taken to be time independent. So we can solve this as a time independent problem, but we won't right now. The solutions here form a complete orthonormal set of solutions. So we can write any new wave function when I, let's say, modify the potential a little bit. I can still write the solutions, the eigenfunctions of the new potential, in terms of the original wave functions. So my new eigenfunctions are chi sub n's. My old wave functions are psi sub l's. And we're looking at transitions, let's say the probability of finding the system in a state psi sub l. So we've got this new set of wave functions that we're writing as an expansion of the original wave functions, and that's all we've done is to substitute it in. Now, from here, there's just some algebra, let's say, actually taking derivatives, going through, and reorganizing things. Then recognizing that the original operator h naught doesn't operate on time, so when I took derivatives, I took the time derivative here, h would come out of that. And that allows me to cancel terms on the left-hand side and the right-hand side of the equation and simplifying this relationship here. In the end, what we are looking for is the time dependence of the probability of finding the particle in a particular state. Again, this is manipulation. What we're doing is actually doing the Fourier transform trick here, multiplying both sides of the equation by psi sub m, multiply both sides by psi sub m, integrate over all space, and we end up selecting out a certain set of functions on the right-hand side. The a sub and m are coefficients. And there's a final result here, which is that the rate of change of the coefficient for the particle in a particular state depends upon the initial state that they started in, and there's a time dependence, which depends upon the energy difference between the two states, and a spatial portion, which depends upon a space overlap between the initial wave function and the final wave function for a transition. And between these two space overlap states, I've got the operator that corresponds to the time-dependent potential that I put in the system. So up till now, what we've done is general, and we haven't made any approximations or simplifications yet. We've said we could do all of these sums, and we can express the rate of change of a coefficient with time in terms of a sum over all of the original wave functions. For an optical transition, the potential that we're interested in is the potential from an oscillating electric field. And for polarization along the x direction, the electric field is just x, E naught, which can depend upon time, cosine kz minus omega t. All right, E naught is the shape of a pulse, and this is the oscillation. I'll give you a graphical example in a few minutes. We take the amplitude to be independent of position as far as the atom is concerned. The atom just sees the field at a particular time, and it doesn't care what it was at different positions. And rewrite the field as a function of space and time in this way. Remove the space dependence, and we just say the field at the position of the atom looks like this. And that's because the atom is usually much smaller than the wavelength of the light. So that's my field, and my potential then is going to depend upon, it's actually the integral of the field, so I might have dropped a minus sign here, but this is the key idea, that the potential looks like the charge of the particle that we're interested in times the field integrated over position, right? Remember, that would be the definition of electric potential. Putting in the electron charge and our original field that depended upon time, and just rewriting it in terms of exponentials, because I'm going to combine this with other exponentials. All right, I've just written the cosine function as using the Euler relation. Then we find that the rate of change of the coefficient for the particle in a given state is this expression, which sums over all of the original states of the system, and depends upon what the original state was, and then what state does it end up in, the mth state here. And then I have an overlap integral, which depends upon the initial state, the final state, and the potential. So that's what I've just written this all out here. Overlap integral. This is sort of unwieldy. What we can do, though, is make a few assumptions. One is that we start the system in one particular state, and so the coefficient for that state initially is high. It's nearly 1. And then look at the change of the coefficient for the initial state and the probability that it transitions into another particular state. And the reason that we can do that is we're going to assume that the perturbing potential is very small compared to the original potential that set the original wave function. So the approximations. For small potentials, one of those A components is about 1 at time equals 0. So we can neglect all of the other terms on the right-hand side except for that one term. And then we're going to ask, what's the rate of transitioning out of the nth state into the mth state? And that, simplifying the previous expression, we've got square root of minus 1i over h bar, a time-dependent oscillation term that depends upon the difference in energy between the two states, just as we had for a sloshing dipole before. Our potential, which is this thing here, and we pulled the time dependence of the potential out of what we had on the previous page and left a space dependence of the potential in here. So this new XMN is called the matrix element for the transition, and it is a spatial integral of the space dependence of the potential and the space dependence of the initial state and the final state. Sorry, initial state and final state. And this is integrated over the volume of the system. It's a space integral. I probably should have written a V here, but I think I decided not to use V because I'd use that for the potential. So now Plugging that back in and manipulating a bit, I find that for a pulse of length t, where the electric field is applied for a time from 0 to time t, the change in probability of a particle being in a particular state and ending up transitioning into another particular state from the nth state to the nth state is an integral over time, right, of what I worked out up here. The electric field amplitude as a function of time. I have an oscillating field, h bar omega t. I have a difference in energy between the two states. And I have a plus and a minus because cosine has got two Euler components. And then a spatial integral. So there are really two integrations going on here. A spatial integral for the matrix element and a time integral, once I know the matrix element, to figure out how we transition from one state to another. One of these terms corresponds to the absorption of a photon, and the other term corresponds to emission of a photon. And it turns out in this perturbation theory that an electromagnetic wave incident upon a system has essentially an equal probability, an equal rate of transition from a low state to a high state as it has for a high state to a low state. We have both absorption and what is called stimulated emission. That is, light comes along and it actually causes the system to transition from a higher state to a lower state. In order to actually assess this, do the time integral, we need to know E0 of t. And I have chosen here to do an example where the amplitude of the electric field as a function of time is a pulse that just turns on and off. All right? So square pulse that turns on and off. But it's oscillating at frequency omega in this case. Okay? What does this look like? So here's my probability. It's not probability of transition yet. Here is the amplitude for transition and all the terms that we had before. Our matrix element, which we haven't worked out yet, charge, electric field, and we have now actually done the time integral for a cosine pulse that turns on and off. So my optical field looks like this. This is the field as a function of time. It's 0, it turns on, oscillates at a given frequency, omega, and then turns off. And when I perform the integral to get this function here, the real part of this function, there's going to be an imaginary part that looks similar to it, now looks like this. I have a maximum in the transition amplitude when omega is equal to the difference in energy between the two states divided by h bar. All right, or h bar omega is equal to the difference in energy between the two states. And we have a probability in the end of emission and of absorption. And that's what corresponds to the positive and negative omegas here, emission and absorption. We actually want the probability that the system transitions, and so we square the change in the amplitude. That should be change in amplitude. So squaring it out actually gives us our familiar sinc function. And so in the end, the transition probability between two states looks like field strength squared. So yeah, the transition rate depends upon how strong the field is, at least in this weak approximation. A matrix element, which we're going to talk about in a few minutes. Time squared, that is, the longer we leave the signal on, the higher probability that a transition occurs. And then sine squared, I've written this as beta, where beta depends upon the energy difference between the two states that are transitioning and the frequency of the light that's actually incident upon the system. So this is just a short form here. So sine squared beta over beta squared. And that has the standard shape that we have learned from diffraction theory, for example, where we have a large maximum. In this case, that maximum occurs when the frequency h bar omega is equal to Em minus En. I just happen to set that here. And interestingly, transitions occur even if the exciting radiation is not exactly at the difference in frequency between, at the difference in energy between the two states. Right? H bar omega doesn't have to be exactly equal. The transition rate is a maximum when it is equal to Em minus En. But we can be off by a little bit, and we can still induce a transition. All right? That idea there that we can be off by a little bit and the transition still occurs is actually deeply related to the Heisenberg uncertainty principle. So what have we learned so far? 1. Probability that we find a system that starts in a state N and finishes in state M is a maximum if the energy difference between the two states is equal to the excitation frequency of the light that's incident on the system. That's no surprise. Probability of transition increases with time, and it increases with electric field amplitude. That's no surprise. This one's a bit of a surprise, that transitions can be induced that either go up or down in energy. If it's in an upper state, then incident light causes it to go down. If it's in a lower state, then incident light causes it to go up. Absorption or emission. And then finally, a little bit of a surprise that the transitions can be induced for frequencies other than exactly h bar omega equals the difference in energy between the two states. Shorter times yield wider frequency ranges. Longer times, narrower frequency ranges. And this is a version of the Heisenberg uncertainty principle. All right, so that's we've just pulled out the time and energy dependence of the probability of a transition occurring. We actually still need to assess the spatial integral, and that's the part that we talked about earlier on in this lecture. So what are some of the ideas that come out of the space integral? Remember that we had a product of x, mn, and the time portion. So now we'll focus on the space part. The spatial matrix element for linearly polarized incident light, where the incident light is along the x direction, is the integral over space of the final state spatial wave function x operating on the initial state wave function, the spatial portion of the wave function. And this integral is actually just like the integral that we got for our semi-classical approximation analogy at the beginning. So if the initial wave function and the final state wave function have the same parity, then the product of those two wave functions will be even. And when integrating over x, we'll find that the integral is 0. So multiplying the even function by x, y, or z, depending upon the polarization of the light, yields a matrix element here, which is 0. So all of the energy stuff that we talked about before, that transition is not going to happen if the initial and the final state have the same symmetry, the same parity. If they have different parities, odd and even, for example, then this matrix element will actually exist. So the rule that comes out of this is that the parity of the initial and final states must be different in order for an optical transition to occur. Here's an example. I've got some states here for a particle in a box, and then I've got some states for a harmonic oscillator to serve as examples here. So the ground state is an even function about the center of the box. The first excited state is an odd function about the center of the box. Second excited state is an even function, odd. So even, odd, even, odd. Transition cannot occur from an even state to an even state, or from an odd state to an odd state. So right away we can predict that we won't see those transitions if we could do optical spectroscopy on this system. We will see transitions from even state to odd state, even state to odd state, or odd to even, for example. So we can look at this system and right away tell whether we're going to see optical transitions between a given pair of states. Same argument here. I've got the ground state is even function. First excited state, odd, even, odd, even, odd. They look a little different from these because of the symmetry of the details of the potential. But the potential itself is symmetric. It's an even potential. And we only get even and odd wave function solutions. So again, we can predict which transitions we might be able to see between the electronic states of a harmonic oscillator. All right, we'll take another look at that space integral. What I showed on the previous page was an integration just in one dimension given a one-dimensional wave function. But our wave functions for atoms are very frequently spherical wave functions. So let's think of this in spherical coordinates now. And first thing I'll do is consider the angular integral in theta. The Legendre polynomials are eigenfunctions of the theta part of the time-independent time-independent Schrödinger equation for any spherically symmetric potential. So my wave function is going to have a form like the Legendre polynomials, in theta at least, and associated Legendre polynomials. So those are going to end up being polynomials that are even or odd in cosine theta. The matrix element then is going to look like this. We're going to be integrating theta from 0 to pi. That means that the actual thing, when I talk about even and odd, it's p of x, where x is cosine theta, and therefore this integral goes from 1 to -1. In initial state, final state, right? And then we look at what the potential looks like. Remember, the potential is, or the field in this case, is along the z-axis. And so the potential looks like, it's along the x-axis, so the potential looks like sine theta. And then we can look at the rules for the integrations of the Legendre polynomials, and we end up being able to show, we're not going to do this in any detail, that that integral, this one here for the matrix element, is 0 unless the difference in the L polynomial, the angular momentum for the initial and the final states, is 1. So the angular momentum can increase by 1 or decrease by 1, but the angular momentum must change by 1 for an optical excitation to occur. And I just note here, by the way, that a change in angular momentum by 1 turns out, if you look at it, to be equivalent to a change in parity. I'll show that on the next slide. Here are some images that I stole out of Wikipedia. The s orbital, the L equals 0 orbital, is even in x. That is, that when I go from one side of the wave function to the other, the sign is the same. It's fully spherically symmetric. The p orbitals, L equals 1 orbitals, on the other hand, change sign as you go through the origin. So on one side, for example, I'm taking blue to be positive and yellow, amber, to be a negative wave function. The wave function changes sign from plus to minus as you go through the origin. So these wave functions are odd in angle. The d wave functions, L equals 2, are even about the origin, and the f wave functions are odd about the origin. Just taking an example here, we go from here to there, and the sign changes. So angular momentum in spherical systems, the Legendre polynomials, determine whether your wave function is even or odd about the origin. And the angular momentum selection rule then is equivalent to the parity selection rule. It's just that in one-dimensional systems you don't have angular momentum, so it's easier to talk about parity. In hydrogenic spherical systems, it's easier to talk about angular momentum since that's a quantum number that we actually use. Okay, now what about other potential selection rules? We can talk about M, the magnetic quantum number. All right, we want to calculate the matrix element, and I've actually written out the full matrix element with the dependence upon theta and phi and r for x and the spatial volume element. So the overall xmn is going to look like this in spherical coordinates, right? So our matrix element is going to look like this in spherical coordinates. And we actually just did the integrations in theta, and now we'll worry about the integration in phi. For any cylindrically or spherically symmetric potential, the phi-dependent portion of the wave function is just e to the I m phi. We have been writing m sub l. I should leave that in there, right? And so then we look at the actual integral here in phi and find that for electric field along the x direction, and where phi is measured with respect to the z-axis, that our matrix element will turn out to be non-zero if a difference between the initial state and the final state magnetic quantum number is plus or minus 1. So there's a selection rule for optical transitions for magnetic quantum number. Now, if the electric field is along the z-axis, then we find that delta m is equal to 0. So the overall selection rule for atoms is that the change in magnetic quantum number is allowed to be 0 or plus or minus 1. So here's a summary of the overall selection rules. We have energy conservation, but if the pulse is very short, then the energy doesn't have to exactly match. Heisenberg, all right? Delta E, delta T, uncertainty relationship. 2, on optical transition, dipole transition, parity must change. 3. The change in angular momentum quantum number is plus or minus 1. And this applies particularly for spherical three-dimensional potentials. For spherical potentials, angular momentum is a good quantum number. It might not be a good quantum number in other systems. But for all atoms that we work with, then delta L equals plus or minus 1 is a good rule for optical selection rules. And then delta M sub L can be 0 or plus or minus 1, depending upon the polarization of the light. So the parity selection rule applies to one-dimensional and two-dimensional systems. And the angular momentum and magnetic quantum number apply for spherical atomic type systems. And then just one additional note here is that if we worked our way through spin, we would have found that the total spin upon optical dipole transition can't change.